Hello friends, welcome to the video on probability theory by Society of Artificial Intelligence or SOAI. I am Ritul and these slides are prepared by my colleague Tushar. Let's start. So first of all, it's the intro section in which we are going to go through the intro first. Here for any event A, probability of A which lies from 0 to 1 and it is greater or equal to 0 and smaller than or equal to 1. If A1, A2 and so on till AN are disjoint events, that is AI intersection AJ is equal to phi. Probability of union AI is equal to sigma I P probability of AI. The probability of the union of all the events is equal to the sum of individual probabilities of those events. Probability of union AI is equal to probability of AI plus probability of A2 plus probability of A3 plus probability of A4 plus probability of A5. If all the universal set containing all the events, then probability must be equal to 1 and is equal to 1. For example, when I say the ball is going to be any of the 5 colors which are present on the ball, it's always gonna be true, hence the universal set is always 1. You can see this here. This graph shows the universal set in which A1, A2, A3, A4, A5 belongs to a set. Random variable intuition. We will understand this topic by taking an example and later coming to a conclusion. Suppose a student gets one of three possible grades in a course A, B and C. One way of interpreting this is that there are three possible events here. For example, to find probability of A, we take number of students with A grade divided by total number of students. Another way of looking at this is that there is random variable g which maps each student to one of the three possible values. You can see in this graph. Here are grades A, B, C and these are the students and the grades of the student belongs to A, B or C. The random variable g is treated more like a function that serves to map a student to a grade, and we are interested in probability where g is equal to smaller g, where g belongs to A, B and C. The benefit of this is that we can use multiple random variables on the same set to map two different outcomes. This picture is very clear as these are the students' grades belongs to A, B and C and their height belongs to this where height may be short or tall, etc. Random variable formal definition. A random variable is a function which maps each outcome in a universal set of value. In the previous example, G or smaller f grade maps each student in universal to a value A, B or C. The event grade is equal to A is a shorthand for the event. Here, W belongs to the universal set of a function. The grade is equal to A. In other words, all the elements such that when you apply f grades, the function all the elements such that when you apply function grade, the answer is A. Grade is a random variable. Probability of grade is equal to A, which is equal to a set of W belongs to universal set where function is A divided by grade, total number of students. In the context of our example, this is also applies to multi-class classification, mapping one letter to respecting vowel and consonant. Here, it would be the probability of consonant and probability of vowel. Whatever multi-class classification we deal with in real life, they can be converted into probability viewpoint where we are given an input and we try to map it to the other outcome values and we observe the values it can take. Now, random variable in continuous and discrete. A random variable can either take a continuous values, real values, that is weight, height, etc., or discrete values, that is grade, nationality. For the scope of this course, we will mostly be dealing with discrete random variables, that is probability of vowels, consonants, which all draw from a fixed set of discrete values. Here, probability distribution. Consider random variable g for grades. Probability of grade A is 0.1, probability of grade B is 0.2, and probability of grade C is 0.7. The above table represents the marginal distributions over, that is the probability of every possible values that the random variable can take, sums to 1. We denote this marginal distribution compactly by probability of G. True distribution is the probability of the class being 0 is 0 and the probability of 1 is 1. Further, we find the difference between true distribution and predicted distribution is what we will learn in future slides. True and predicted distribution. Consider the above example. Here, this is the table in which you can see that the probability of A, here G is a grade with A, B and C, and the probability of grade, here the probability of grade A is 0.1 and which is denoted by Y, and the Y cap is 0.2. Here the Probability of grade B is 0.2 and its cap is 0.3. Probability of grade C is 0.7 and probability of grade C cap is 0.5. Here, y refers to the true distribution or the actual probabilities of each value of g, and y cap is the predicted distribution or what we estimate the probabilities to be based on our observations. To measure the degree of correctness of our predictions, we can use a loss function. However, squared error function might not be appropriate as it doesn't factor in some of the basic assumptions of probability theory. That is, probability of g is greater than equal to 0 and smaller than equal to 0, etc. So we must select the different loss function that is more rooted in probability theory, that is cross entropy. Probability theory of certain events. We need something better than the squared error laws. Consider the scenario of a random variable x that maps to the winner in a tournament of 4 teams A, B, C, and D. We stop watching after the semi-finals, so we are unaware of the outcome. But in truth, Team A has won. Thus, it's a certain event with probabilities. Probability of A is equal to 1, probability of B is equal to 0, and probability of C is 0, probability of D is also 0. You can see this in this table where X is a team which are A, B, C, and D, and the second column true distribution unknown to us, and y cap is the predicted by us. So probability of team A is 1 is a certain event, and other teams such as B, C, and D is 0. But the probability which are predicted by us are as probability of team A is 0.6 and followed by team B which is 0.2 and probability of team C is 0.15 and D is also 0.15. Before the tournament's completion, based on the point we have watched till semi-finals, we can predict the probabilities of each team's chance at victory. Probability of A is 0.6, probability of B is 0.2, probability of C is 0.15, and probability of D is 0.15. These are the probabilities which are predicted by us. Why do we care about distribution? Consider the signboard with the text Mumbai. Now, our classifier is analyzing the text character by character, and a random variable char maps the character to one of the 26 possible characters in the English language. For the first character M, we know the true distribution intuitively. Here, there are three columns. The function column is about char, which is A, B, and so on to M and so on till Z, and Y is the probability of char, the certain event or true distribution, and the third column is the Y cap, which is obtained from model. Here, let's talk about the second column, which are true distributions or the certain event. Here, the probability of character A is 0 and probability of character M is 1 and probability of character Z is also 0. And when we see the Y cap, that is probability of obtained from model, here the probability of char A is 0.01 and the probability of character B is 0.01 and probability of character M is 0.7, which is the highest, and so on. We compute the difference between the true and predicted distributions using squared error laws or some other loss functions. From this, it is clear why we use distributions in the scope of our learning. We will further see the use of laws with the sigmoid function. Thank you.